Assalamualaikum warahmatullahi ta'ala wabarakatuh and good morning. I'm Dr. Sabak Bau from the Physics Section, Pusat Pengajian Pendidikan Jarak Jauh, University Science Malaysia. This is course JRF 318, Quantum Mechanics. We are in Chapter 1, Introduction to Quantum Physics. This is Unit 1.6. The topic is on wave-particle duality. The objective of this lesson is to describe the wave-particle duality of light. So after we had discussed photoelectric effect, Compton scattering, black body radiation, so we have one big question. Is light a wave or a particle? Okay. In classical physics, light is considered as continuous wave. So we have the Huygens wavefront principle, which we use to explain the scattering, the interference, the refraction of light, and the wave theory is capable of explaining the phenomena. But in microscopic physics, such as in photoelectric effect and Compton scattering, the phenomena can only be explained if light is considered as a particle. So we have this dilemma whether light is a wave or a particle. So the photoelectric effect and Compton effect provide evidence that light acts like a particle with energy E equal to h nu. However, this does not eliminate the results of classical optics, which light behaves like a wave. That means if we have a mirror, the reflection, or if we have a block of glass, the refraction, and so on and so forth. If we do Young double slit experiment, the interference patterns are all there. I mean, we cannot say that those experiments cannot be used anymore. And in order to explain those phenomena, we have to consider light as wave. So, in other words, we cannot dismiss or cannot eliminate the wave properties of light. So, what we have to do? We are forced to accept the idea of wave-particle duality. That is, light behaves sometimes as wave and sometimes as a particle. We have to accept this. Okay? Instant experiment, we have to consider light as wave. Instant experiment, we have to consider light as particle. So, what is photon, which was proposed by Einstein when he used the hypothesis, used the Planck hypothesis? It is a wave, but in the form of packet of wave. Okay, this diagram I took from a book. So, we have continuous wave. Okay, on the left here, continuous wave with different wavelengths. If we add several of these waves at different wavelengths together, it will produce an interference patterns, and which begin to localize the wave. That means, if you remember in wave optics, when we add wave with different frequencies, we have what we call as beat. Remember? BEAT, beats. If we have interference of two waves with different wavelength, If you add some more wave with different wavelength, finally you just get this type of packet of wave. That means it's now like a bundle of wave like this with lambda average and the average wavelength as usual, and it is localized in the sense that it's not stretched to infinity but localized to a distance of delta x. Okay, but however, whatever it is, this wave pattern or wave packet obeys this delta k multiplied by delta x equals to 1. Delta k is 2 pi per lambda, remember that. So now we can see that even though it is a wave, but it is localized. It's like a, a bunch of particle or just like a particle. That means one lump of particle. Okay, even though it is in the form of wave. This is what we call as localized wave. So we have now in our hand the classical physics which consider light as wave in reflection and refraction of light in diffraction, now of course in electromagnetic wave using Maxwell equations. But on the other hand, now in quantum physics, we have to consider waves as particles or photons as proven by blackbody radiation, photoelectric effect, and Compton scattering. So this is what we call a wave-particle duality. That means light have both property, that is wave properties and particle properties. As a conclusion, light has both wave-like and particle-like properties. Thank you very much for your attention.